The memoryless property concerns the property of random variable. Not all random variables, very limited amount of random variables. So what is the memoryless property? Well, if x is the non-negative random variable, we say it has the memoryless property if, and then this expression, it's a conditional probability you note, then equals to a unconditional probability, where s and t are bigger than or equal to 0. Interpretation, we want to kind of look at this, we want to interpret this thing before we actually go and prove it, but to be able to interpret it, it would help if we know the following, that the only discrete random variable that has this memoryless property is the geometric. Let's just say discrete random variable is only the geometric distribution that has this. And continuous random variable, non-continuous random variable, only the exponential distribution. The exponential distribution has this property. So there's only like 2 distributions that has this property. Okay, let's talk about what this means in the context of a geometric distribution. Before I do that, let's just say, so I'm going to talk about, give you interpretation of this equation in the context of geometric distribution, and then for an exponential distribution, and then we're going to prove it, that geometric distribution has this property and exponential distribution has this memoryless property. Okay, interpretation first, because no point doing the proof if we don't even know what this thing means. Geometric distribution. Recall that the geometric distribution is to do with the number of successes, the number of trials until we get our first success, or it could be defined as the number of failures until we get the first success. Okay. So in that case, let's just say let x be the number of trials until we get the first success. As an example that we all understand, a boring example, nevertheless, it's, let's say that we've got a coin. How many times do we have to toss this thing, throw this thing up in the air until it lands on a head? Then what this says, conditional probability says that if you haven't already got a, so x is the number of trials until you get a head. If you haven't already got a head within t tosses, the chance that you get a head occurring s tosses after another s tosses is the same as if you started afresh from the start. That's the same as the chance that you've just get a head after s tosses. So to put it another way, you've thrown the dice t number of times and you haven't got a head. So that's this, this number of trials to get a head exceeds this number of tosses. So you've thrown it t times and you haven't got a head. The chance that you're going to you need at least another s throws to get that head is the same as if you just started from the beginning, that you need at least you need more than s throws to get ahead. In that respect, the fact that you've already thrown it t times is neither here nor there in getting ahead in at least another s throws. That's what this is saying. So basically it's forgotten that you've already thrown it t times. If you need at least another s throws to get ahead, it's the same as if you did it from the start. In other words, it's a bit like a goldfish memory. It kind of forgets. Right, similar thing with the exponential, and you'll see the story is very similar. So, okay, the exponential distribution is used to do with like a waiting time until the first event occurs. So let's pick one that you all understand. Let x be the time you've been at college until you get your first date. This says that if you haven't already got a first date within t time period, that you have to wait another s periods beyond t to get your first date. Is the same as if you as waiting for at least s periods from the start of college. In other words, it's forgotten that you've already been at college t period t. Waiting at least s periods after t is the same as waiting from s period from the start. And then we can kind of see that both these, so these two distributions are very similar then, aren't they? They're to do with, this is to do with number of trials until the first success. This is to do with the waiting time until the first success. Once that something happens, it's game over. Okay, now I'm going to kind of prove it first for the geometric, and I'll do it two ways. For each of these, we can do it in two obvious ways. And the method, you don't have to do both methods, but I'll just talk about the method now, because it's up to you which one to use. Let's see, method 1, we can prove these using a cumulative density function. And method 2, we can use the probability mass function for the discrete case and the probability density function. Okay. So which method do we use depends on what we know about. Do we know the CDF of these two guys, or do we know the probability mass or the probability density function of the two guys? And just to say, it's going to be less work using the CDF. But first we have to know what the CDF is, and that might be something that is not provided to you in the exam. It might be that you're given these guys in the formula sheet in the exam. Okay, so let's start off first with geometry. Basically, for each of these two, I'm going to do the same thing. First, let x follow the given distribution, and then note what the CDF is, or PMF or PDF, depending on which method I'm going to use, and then obtain an expression for the left-hand side. And I'm going to do the same by obtaining an expression for the right-hand side, and then say left-hand side equals the right-hand side. Done. In case, just one more thing before I go to the proofs. In case any of you are asking, well, are these two events independent? Say this event A, this event B. You should be clear that these events A and B are not independent, because you know that if A and B are independent, given that B has happened, doesn't affect probability of A, so it would just be equal to probability of A. And this is not what this expression is saying. And here it's quite obvious why A and B are not independent, because they're both kind of to do with time t. Alright, geometric. Let x be a geometric parameter p, probability of success in a single trial. X is geometric parameter p, as said. We're going to define it where x is the number till the first success. The alternative way is where x is the number of failures till the first success. Alright, so if we write it this way, the CDF for geometric, let's just write it down here, is equal 1 minus, before I do that, let's just rewrite this in terms of the different notation, so you can probably, this is more concrete to what it means. Okay, this means this, probability x is less than or equal to a, and for geometric that is 1 minus probability of failure, and you failed a times, so where q is equal to 1 minus p. Okay, now the left hand side of the expression of that memoryless property, which says probability x is bigger than s plus t, given that x is bigger than t, let's rewrite this. It's conditional probability, so we're thinking about that we know that these two guys are not, from the result, are not independent. We use the formula that connects this conditional to the joint and the marginal. So this is this event here, x bigger than s plus t is an event. That's like my a, and the b is like x bigger than t. Alright, so imagine this is, if it helps you, this is like my a given b. This is therefore my a intersect b. and we want all that over the marginal of x bigger than event x is bigger than t. Okay, right, so we look at this guy and we think, what do we do? So let's look at this top one, and let's call this thing star, so we can refer back to together. Now probability x bigger than s plus t and x is bigger than t, does that simplify? It means that the number of trials for the first success is more than t, and it has to be also more than s plus t. So if we have a little line here, a number of trials, 1 trial, 2 trial, 3 trial, and so on. So x here is the number of trials, t trials. So x is bigger than t, so we have to shade all this. Well, we should actually shade each t plus 1, t plus 2. Right? This is basically my Venn diagram. But we also have to have, at some point, it's going to be t plus s, and this means x has also got to be bigger than t plus s. So we shade in where that's the case as well. So it's got to be that one, t plus s plus 1, and so on. And then what the intersection means is that it's where we shaded both regions. Well, it's this where we shaded both regions. And on and on. In other words, what we've got here is probability x is bigger than s plus t. That's the case when these two statements are true, that x is bigger than t and x is bigger than s plus t. Right? Because remember that s, t are non-negative. So this thing here is bigger than that thing, but x has got to be bigger than, it's got to be bigger than this, and it's got to be bigger than that number. So it's not as, I feel I'm making it more harder than it is. Let's just say t is 2, s is 3. So x is bigger than 5 and x is bigger than 2. Well, if x is bigger than 5 and it's bigger than 2, it's got to be bigger than 5. So that's all I'm saying. Alright. But this, you can see here, you should look at it and think, that looks like something to do with PDF. And it is, because this guy here is 1 minus probability x is, if I write it this way, because remember CDF is to do with less than or equal to, this is guy is less than or equal to s plus t. So the opposite of this basically is this, is 1 minus the opposite of this. So 1 minus of this is saying that x has got to be bigger than s plus t. Right? Remember that because x is discrete, because it's geometric and geometric random variable is discrete, that bigger than and bigger than equal to mean different things. So I can't replace this by less than, because that would mean different things. But this thing is now in the form of a CDF. So I know the formula for CDF is here, so I just substitute that in. So I go 1 minus, and then 1 minus q to the power of s plus t. This is my CDF bit. Take 1 minus that through the bracket, and so you can see that's going to be qs plus t. Okay, let's call this 1. So that's the left hand side dealt with. The right hand side, we don't actually have to calculate anything, because you can just say analogously, if we did this from here, you can see that probability of x bigger than t is just going to be q to the t, because it's got to be of the same pattern. From here goes to here. So basically you're just doing the power of whatever this is. This is the same pattern, so you just say that. Alright? You can say it in a likewise fashion, so that you understand that you haven't just made it up. Okay, likewise fashion. Something like that. So let's call that 2. So we just say 1 and 2. We substitute that now into star. Oh, hang on. No, that's not. Oh, sorry, that's not the right hand side. That's the bottom bit of star. And I should say that. So 1 and 2 into star. So now I've got the top bit and the bottom bit. So I've got this expression. And you can see that probability of x bigger than s plus t, given that x is bigger than t, is equal to q to the st over q to the t, which is qs. And what I meant to say earlier is that now the right hand side is exactly, you can do it in an analogous fashion, in a similar fashion to the above. You know that the right hand side is property x bigger than s is what we want, but we've just done all that calculation above, so it's a similar kind of thing. So what we get is q to the s as well. Hence we say that left hand side equals to the right hand side, done. Okay, so just look back on it, that this is what we wanted to show. This left hand side is here. The right hand side, left hand side is here. And the right hand side is here. And we'll just say, look, they're the same, done. And if we look at the expression, it kind of makes sense because q is like probability of failure. So q to the s means that you've failed s times. So if you this says that the chance of you succeeding, you need at least s attempts to get a success, is same as saying that you failed s times. So your success has to be beyond s number of goes. Okay, next we're gonna now turn to method 2 for the geometric, and I'm going to use, just that you can see it, we're going to use the probability mass function. So if x is geometric, parameter p, where I've defined x the number of trials until the first success, then what this is, it's you failed, say, x minus 1 times, and then you get your success. So that this is the probability mass function. Okay, so I'm going to do the same thing now. I'm going to prove this thing. So the same argument as before, probability of x bigger than s plus t given that probability. X is bigger than t, this is the left hand side. Let's just put it now so we can see what they're saying. Is equal to probability of x bigger than s plus t and x is bigger than t, or probability x is bigger than t. Take the top bit here, probability of x bigger than s plus t. I know I do have to repeat all this again, but I'm just doing it so that it's kind of familiar to you. Same as saying x is bigger than s plus t, so now going slightly faster. What is probability of x plus t using the PDF? Well, it's beyond s plus t number of goes. X is discrete random variable, so it's summing, and what you want is the sum of the probability of x given x from x is equal to s plus t to however many goes, which is unlimited, so it could be infinity. So now we substitute for this guy into here. And I'm sure at this point some of you will begin to switch off the video because you say, oh no way, I'm not going to do it this way, which is perfectly fine. But in case you're interested, two terms multiplied together, or two components of the term multiplied together, only one depends on x, so using the fact that p is a constant as a common factor, we can drag it out to the other side. So that's p sum s plus t q to the x plus q minus 1, sorry, q minus 1, like this. And now what? Now what is now working? We want to go back and just check whether we've done anything wrong. So we know that this is true. X is bigger than s plus t. X is discrete, so bigger than or equal to mean different things. So if I look down here, I can see that I am not summing over the right thing. Because x is bigger than s plus t, it must mean that therefore it's bigger than or equal to s plus t plus 1. So the first smallest value it can be is s plus t plus 1 plus 1 plus 1. So I hope you spotted that. Did I do it on purpose? Well, no. Let's see. So if you wanted to express this some more, you could have said for sure like t plus 1, okay? Don't need the step, but it helps to see that smallest value of x is s plus t plus 1. Now that looks fine. Okay, well, we've got this infinite So it's like a GP, isn't it? It's an infinite one, except for instead of starting at 0, we're starting at a point which is not 0, because we know that if this started at 0, then it'll be of the nice form, because q is a number less than 1. We know something like this is equal to power I is 1 minus a, isn't it? So we would like to use this result, but we're not starting at 0, so we want to make a substitution for this. So what we want to say is something like let j equal, and then just take all these guys to the left hand side, x minus s minus t minus 1. So why do we do that? Because if you do that, then the smallest value that this will be, it's got to be when x is equal to that. But if x is equal to that and you take this over to the other side and subtract it, the smallest value of j will be 0. And then j will run to infinity as well, because this is x goes up in increments of 1. So if that thing is infinity, this guy isn't going to kind of control that guy, so it's still infinity. So anywhere we see x, we replace it. We kind of rearrange it. So here we have q to j, isolating x, taking st1 over to the other side. We have j plus s plus t plus 1 minus 1, because remember about that guy here, put that in brackets, so you can see that the 1's are going to cancel. So if you allow me to do that, let's just rub that out. Didn't need that step there. Okay, so this is what I have. And what can we do now? We obviously cannot get a numerical answer because we don't know what p and q's are. So where do we stop? We can see that this is the power of j plus s plus t, but which we can rewrite as, let's do it on the side because it's not real. It's something you. This is same saying q to the j times q to the s times q to the t, or s plus t, yeah, using the kind of rules of powers of exponents of these numbers. So what I can say is that basically we've got this q. I've split it up so that there's terms involving j which are kind of summing over, and terms which do not depend on j, constants. So that's the reason I did this step. And then the constant can come out, so we've got q s plus t, and then the sum q to the j, which I obviously know is 1 over 1 minus q. Alright, so we could actually replace this now by 1 over 1 minus q, and then the q cancel one of those q's there. But I don't want to kind of do that because I don't think it's going to add anything. Let's then look at the bottom part of the expression of this left hand side. So we don't actually have to do anything because it's of the same shape. So this probability x is bigger than t is going to be equal to probability sum j equal to 0 q j plus t, which is equal to, I could have just done that, p q t sum of j equal to 0 q j. Right. You can see why I didn't bother to write that, because I can see a lot of these two are going to be the same, they're going to cancel. Therefore, the left hand side is, and just basically 1 divided by 2, expression 1 divided by expression 2, and you can see that's going to be qs. Let's call this star. Right, I told you there's a little more work with the PMF, probability mass function. But we've done all the hard work, because now the right hand side is in similar kind of fashion. Right hand side we want probability x is bigger than s. And just looking at the pattern, it's the same thing, so it's just p q to the s, sum from j equal to 0 to infinity q to the j, which I want this to come to q to the s, so now I do make the substitution. This is a infinite geometric progression, and it works because q is less than the value of 1. So this is going to be 1 minus q, like so, right? And then what do we say? But 1 minus q, 1 minus probability of failure is the same as probability of success. So in other words, it's same as saying P. P's cancel. Call it double star. Star left hand side equals double star. Done. Now to show in a similar way the memoryless property for an exponential. So let x be an exponential with parameter lambda, and we know that then x is bigger than 0, and it is continuous, so bigger than or bigger than equal, it's neither here nor there. Alright, so what do I want to do first? Method 1, proof of the memoryless property. Let's do the CDF one. So first let's write down what is meant by what is the CDF for the exponential. So it's property x is less than or equal to a, and that is equal to something that you've proved before. If you haven't proved it before, it's in textbooks. Okay, there you go. That's what we have. Right. Let's do it. Left hand side. So it's probability of x bigger than, well, just in case there's people just watching this video without watching the proof for the last one, the geometric. Let me just kind of do this quickly again. So the left hand side is s plus t, and x is bigger than the numerator part over t, over probability x is bigger than t. Okay, which is equal, saying that x is bigger than s plus t and x is bigger than t is the same as probability x is bigger than s plus t. A reason I gave more detail in the video for the memoryless property of the geometric of the probability that x is bigger than t. So this is what we want. Star. Okay, now top bit. Probability x is bigger than s plus t using the CDF is the same as saying 1 minus f of s plus t, i.e. 1 minus, because people are not comfortable, sometimes students are more comfortable with this terminology. X is less than or equal to s plus t, right? That's the same as f of s plus t here. Okay. If you're wondering where that came from still, just know that probability of A is equal to 1 minus probability of not A. Right, that's what I'm doing, opposites. X is bigger than that, x is less than that. Less than or equal to, I don't want to confuse you, so it's continuous, it doesn't really matter where I put less than or equal to, let's just put less than. Alright, okay, so I can substitute now straight into that here. So it's 1 minus e to the minus lambda s plus t, which is equal to e to the minus lambda s plus t. Call this 1. So that's the top bit evaluated. The second bit, you can just look at the pattern and see it's the same. Look, this is bigger than a number. It's going to be e to the minus lambda and that number. So therefore the bottom part is x bigger than, probability x is bigger than t is just going to say e to the minus lambda t, 2. Okay, so this is like 1 over 2 in my notation. So we'll just say, so 1 over 2 divided by 2 is equal to that divided by that. You can see we're just going to be left with e to the minus lambda s. Okay, let's call this 3. And now we've got to look to, so that's the left hand side dealt with. Now the right hand side of the memoryless property, we want probability that x is bigger than s. But we don't have to do anything because it's just going to be, it's off this form, so it's e to the minus lambda s. Let's call it 4. Now 3 equals 4. At the left hand side, this whole thing is the left hand side, is 3. This is the right hand side of the memoryless property. So in other words, the memoryless property holds. So we're done. Method 2 for the memoryless property of an exponential, we're using the probability density function. So x is exponential parameter lambda. We have the property density function f of x, which is continuous, is lambda e to the minus lambda x. Okay, for x is bigger than 0. Bigger than or equal to 0. It doesn't matter because x is continuous. Okay, similar, same thing as before. The left hand side now we can just say is probability of x bigger than s plus t divided by probability that x is bigger than t. And so we'll look at each of these guys. So first, probability that x is bigger than s plus t is equal to, want to integrate this PDF with respect to x of x from s plus t. Where's the upper limit? Well, it says bigger than 0 can be, so it hasn't got an upper limit, it's infinity. So that's what we want to calculate. Substitute this thing and calculate this integral s plus t. Okay, so put this into here. You can see lambda comes out, e to the minus lambda x dx. At this point I know it involves integration, so I slow down because people are often fearful of it. So let's do it. Lambda is constant. And then we have, recall the rule, integrate e to the ax dx is equal to 1 over a e to the ax plus a constant of integration. So what we have here is minus 1 over lambda e to the minus lambda x infinity s plus t, which is equal to, I take this is a constant, so it actually come out there, so you can see lambda's cancelled, we've got a minus sign, so let's put the minus, the big brackets, and then we substitute each of these guys in. Now, because infinity, I know for stats, you probably find if it's a first stats course, just substitute x for infinity. But since infinity is not a real number, we should be taking limits. It's the limit, say, of r tending to infinity of e to the minus r lambda, and minus, and then substitute this into there, minus e to the minus lambda s plus to the t. That's what we want. But in the limit as r tends to infinity, okay, e to the minus infinity, that's going to obviously tend to 0. Tend to 0, isn't it? Or since I've written it with a limit there, I should put equal to 0. That limit is 0. Minus and a minus, that's e to the minus lambda s plus t. That, okay. And similarly, for the bottom part, similarly, you can just see directly that x bigger than t is going to be e to the minus lambda t. So again, just saying that the left hand side then is 1 divided by 2 e to the minus lambda s. Okay, and the right hand side doesn't require any more working. Essentially we're done. It is probability that x is bigger than s. It takes this form, so it's e to the minus lambda s. These two are the same. Hence, left hand side equals the right hand side. Left hand side of the memoryless property equals right hand side of the memoryless property, and which will be remembered what these things are, and we are done. Okay, so we've done 4 proofs for memoryless property for geometric and exponential. Just to recap, for the discrete, among the discrete random variables, it's only the geometric distribution has this memoryless property, and of the continuous random variables, only the exponential distribution has this property. For each, we've done 2 proofs. One method using the CDF, and the second method using PDF for continuous case, or PMF for the discrete case. Alright, so there you go, and if you pardon the pun, let's hope that you remember some of this. Okay, take care.